Imagine we have a bunch of data points and we want to train a regression curve to predict the value of y given an input x. The usual approach is to divide the given dataset into three different sets: the training set, the validation set, and the testing set, which we have represented in green, blue, and red colors respectively. We first train our model on the training set. After some training, we check its performance on the validation set. If we find problems like overfitting or underfitting, which we will discuss in a minute, we tune the hyperparameters and try again. Now, if the performance on the validation set is good, we can use techniques like early stopping to prevent overtraining and save computation time. Finally, once the model is fully trained and tuned, we evaluate its final performance on the test set. This gives us an unbiased estimate of how well the model is likely to perform on completely new data. Now imagine we have some data points, and for a moment, let's keep the test set aside. When we train a model that does not perform well and gives poor results on both the training set and the validation set, this situation is called underfitting. It means the model is too simple or hasn't learned the patterns in the data properly. On the other hand, if the model performs perfectly on the training set but fails miserably on the validation set, this is called overfitting. In this case, the model is too complex, has learned even the noises and random fluctuations in the training data instead of true patterns. A good model should train just well enough to achieve low error on both the training set and the validation set. Remember, if the model has high training error and high validation error, it's underfitting. If it has low training error but high validation error, it is likely overfitting. Now, the validation set is used to tune hyperparameters such as the learning rate, batch size, or the number of layers, which do not have a fixed rule for predetermination. And if you are not familiar with these items yet, don't worry, we will discuss them in future videos. Now to summarize, the training set is used to train the model and update its weight. The validation set is used to tune hyperparameters and decide when to stop training, for example, using early stopping if the model already performs well. The test set is used at the very end to evaluate the final performance of the model on unseen data. So, the life cycle roughly looks like this. We start with the dataset, split it into training, validation, and test sets, train the model, validate it, if needed, tune the hyperparameters, and continue training. Finally, once satisfied, we stop training and check the performance on the test set. Now, there is no strict rule on how exactly we should split the dataset. A common practice is, if we have a lot of data, we usually use around 70% for the training set and split the remaining 30% between the validation set and the test set. If we have less data, we might use a 60-20-20 split. This way, we still have enough data for validation and testing to make sure the model does not simply memorize noise or random patterns. The main idea is to ensure the model gets enough data to learn from, while also having separate data to properly tune and evaluate its performance. When a model performs poorly on both the training set and the validation set, we say the model has a high bias. This means the model is too simple to capture the underlying patterns in the data, leading to underfitting. On the other hand, when a model performs very well on the training set but poorly on the validation set, we say the model has a high variance. In this case, the model is too complex and has essentially memorized the training data, including the noise and outliers. This leads to overfitting. The goal is always to reduce both bias and variance. But in practice, this is very difficult to achieve at the same time. This is because bias and variance have an inverse relationship. When we reduce variance, bias tends to increase, and when we reduce bias, variance tends to go up. So, the key is to find the right balance, not too simple, not too complex, to achieve the best possible performance on new unseen data.